Hey, good afternoon. My name is Kelch, and I lead a product management team at Amazon for food and product safety. So we create and maintain a portfolio of products to do many of the same things that you guys do. So we listen to customers, we investigate defects, we qualify suppliers, and in some cases we recall products. And we also do several things which you may not do, which is what we're here to talk about today. So yeah, today we intend to teach you about Erica, which is our machine learning tool to identify products with potential safety risks to enable us to take action before bad things happen. This machine learning process allows us to better serve and protect our customers. And essentially, how we do that is by taking potentially unsafe products, which otherwise appear to be free of defects, off of our website. And so the action that we initiate is actually an investigation. And these investigations rely on human assessors, subject matter experts who are specialized in a particular domain or product type. And so what our machine learning process does really has nothing to do with simplifying the critical nature of those roles. But what it does is it prioritizes the work that they do to focus on high judgment activities rather than low risk or isolated issues. So what is customer risk? So customer risk for us, even though we run over 1 billion calculations a week, is not an index or number. We spend a great deal more time focusing on the actual customer than we do on algorithms. So we read every day customer feedback that's detected by our process and customer feedback that's missed. And these pieces of information are much more vivid than detected topics or elevated risk scores. And so on the slide behind me, you can see some information from the CPSC about lithium-ion batteries. And they receive several hundred reports per year of issues related to these products. At Amazon, we receive quite a few more than that. And so it's very likely that with you today, these products are in everything. It's very likely that with you today, you have more than one device with a lithium-ion battery. It's even more likely that you have one of those devices in your hand right now. Fortunately, it's probably safe. These devices are predominantly safe. So the issue at hand, the issue at hand is actually the lithium-ion cell, which can become dangerous if it's overheated or punctured. The root cause is usually a lack of manufacturing controls, damage in transportation, really kind of like a drive to low cost. And so what we do, what we do is we actually clustered some of these products together from known issues that have happened in the past to determine the likelihood of risk of all of these products to remove it from the website before it has an opportunity to get in your hands. And so, as you might expect, and we expect, is safety is important to Amazon. We want everyone to trust our stores and shop comfortably on our stores. We also require third-party sellers to comply with all relevant laws and regulations, and then we work quickly to take action on behalf of our customers. So quickly, in fact, that over 40% of our investigations happen before anything ever does occur, if it ever occurs. And so this has been a real shift for us, which is, again, what I hope you take away from the presentation today about how we move from these reactive processes, while quite robust, to proactive processes. And so the message is very simple. It'll get more complex in a few slides, but the simple message is that what you do today does not have to be the same as what you did yesterday. So there's 3 of us here who are going to walk you through really the end-to-end process of the development. And so we're going to talk about the data we use to make these predictions, how we curate and clean that data. We're going to talk to you about some of the key decisions we made while building these models, what drove those decisions. And we're going to, more importantly, talk about how we scaled these predictions from a few Python notebooks to processing over 1 billion calculations a week. And so at the end of the presentation, we're also going to provide several success stories of how this has made a real-world impact. And my specific role today is going to be providing you with the context on our reactive detection, so how we actually detect and listen to our customers, our investigation processes, and then some of the really specific challenges that we faced when designing the system. So again, to give you the proper context, it's important to take a small step back and just understand how innovation really works at Amazon. So, to understand how innovation really works on Amazon, and then you can better understand why we are unsatisfied with the process. It's actually quite robust and rapid in terms of taking things down. So it all starts with our leadership principles, and our leadership principles. So innovation is really driven by a deep understanding of what our leadership principles are and how we internalize that. And so these 14 leadership principles really define what it means to be successful at Amazon, and also to think, act, and operate in such a large company, but all with that day one focus. And so these aren't just words on a badge. We actually don't have these on our badges. Even though they're often on posters, they don't have to be on the walls. It actually takes a surprisingly short amount of time for a new employee to really understand and memorize all of these leadership principles, what it means to index, over-index, under-index, or kind of find that sweet spot in operations. And really, this is how we hire, it's how we manage, it's how we promote. Unfortunately, for our loved ones who don't work at Amazon, it's often how we speak. And so what I'm going to do in the next two slides, I'm going to highlight two of these leadership principles that really speak to why and how we innovate. And so I'm going to, again, kind of violate a presentation 101, and I'm going to read this actual slide to you because we don't paraphrase these leadership principles because each word is so important. They've been heavily scrutinized and debated, and for good reason. So customer obsession, which is most often referenced, is that leaders start with the customer and work backwards. They work vigorously to earn and keep customer trust, and although leaders pay attention to the competitors, they obsess over our customers. And we'll come back to that several times. Now, Invent and Simplify actually has specific language about innovation. So leaders are expected and required to innovate. Leaders expect and require innovation and invention from their teams, and always find ways to simplify. They're externally aware to looking for new ideas from everywhere, and they're not limited by not invented here. And the most important part here is as we do new things, we accept that we may be misunderstood for long periods of time. The reason why that last sentence is so important is because it really gives us free license to gamble and take big bets on new processes, which is exactly what we did here. So before we can predict what's going to happen in the future, first we have to listen to our customers. And so this slide is describing what we've presented externally many times. We call it a customer feedback monitoring. And it's a mechanism that we've invested heavily in to listen to our customers from a variety of sources and detect when something goes wrong or unexpected. And so essentially what we're doing here is we're relying on both spoken feedback, to a customer service associate, written feedback, or sometimes machine transcribed feedback. And so it's fairly direct when you describe an issue to a customer service associate, and they can kick off the workflow for what you're describing. It's not quite as direct when we're trying to infer something from what a customer typed to us, potentially in several languages, and potentially not in the language of that home store or marketplace. And so what we do is we primarily make these data-driven decisions. We have risk assessments on different categories and types of products, and we respond rapidly to these kind of data thresholds. But there's also these rare situations where customer anecdotes really disagree with our risk assessments, where we think that some product is fairly safe, it's low risk, there's isolated incidents, we don't have to react, and then we get a customer anecdote that tells us that our understanding was incorrect. And so we obsessively seek these false negatives to disconfirm our beliefs about these specific areas. And so this native language processing that we use to make these decisions is not a nice to have, it's a requirement, because the volume that's going through this process exceeds 30 million interactions per week. And so this is just not the kind of thing that a person can do one by one by one. And so this also happens in near real time, which is where we kind of move from the far right to the middle column. We have these ML models that are detecting these topics, they're detecting the potential severity, kind of based on keywords, phrases, the context, the sentiment of the sentences. And when we're highly confident or the severity is high enough, we take immediate action. That action can be suppressing and investigating. It can also be investigating and then suppressing. Or for a subset of these actions where we're not confident in the machine decision, we send this to human annotators. And then the human labeler assigns the severity or the topic, which then kind of kicks into the workflow. So then the last column is around resolution. And so essentially what we do here, it's one of the three actions I told you. Ideally, we take the product off the website. If we have any risk or suspicion, our bias is to protect the customer, so we remove the item from our store. An alternative is there's not enough information to take action, so we actually store that for model retraining and risk detection, or in some cases we take no action at all. But in every case, we use this data to train our models and continue to evolve our thinking. And so our challenge might not be obvious to everyone, but we started to see over time that this process, while very fast, very robust, we really weren't missing things. We were actually catching a lot of the same things, and these issues were occurring, but never more than once on a brand, never really more than once on a particular product, or even a source, whether it be like vendors, distributors, third-party sellers, because all of our processes were essentially treating each product as unique. And we have billions of products that we're all treating as unique. And so finding these outlier products in our whole galaxy of selection was not easy. And we weren't able to do it with simple rules and thresholds that we were defining internally. So we needed to find a better way to identify these clusters of risk. And so depending on kind of your background, the space you're operating in, you can frame this in a bunch of different ways. You could say, hey, this is a CS, customer service engagement issue. Maybe there's something better we can do to resolve the customer's issues, kind of make them whole, make them happy. From an operations perspective, you could say, hey, maybe we should put some inbound processes. We should inspect these products. Or you can say, hey, from a seller qualification, we can really kind of ratchet up the friction that's required, more testing documents, etc. But the reason I read that customer obsession slide earlier is because this was never a decision point for us. It didn't even go through our minds. We really started with the customer experience and worked backwards, and we found the defect in that very robust process I just described to you. And that defect was that something bad had to happen to initiate an investigation, which is kind of like was our fatal flaw. And so what we also did was we said, hey, these billions of products are not unique. In fact, they're all related, and there's processes, especially in machine learning, that we can calculate the relative distance between products. And so what we were able to do, and we're going to describe in a few slides, is cluster these products together and risk assess clusters of products and how that risk changes over time to calculate essentially a real-time risk score for products, which has allowed us to move from the domain knowledge and curiosity of SMEs to a very quantifiable risk score. And so what is Erica? And how do we see into the future? So you can be forgiven if you haven't seen one of my favorite movies, which is the 2002 visceral and thought-provoking Minority Report. And in Minority Report, Tom Cruise is part of a special police division, and I couldn't use the artwork that I wanted to, which is the actual movie poster. But in the movie, Tom Cruise leads a special unit in the police department which arrests criminals before they commit the crime. And Erica is exactly the same, except that you need to replace the oracles and psychics with linear algebra and criminals with consumer electronics. And so the other thing to consider here is these machines and our processes, our models, they can't actually assess the risk of a product. But fortunately, internally, humans have done this hundreds of thousands of times at Amazon. They've assessed the risk and taken action or not taken action, over the last few decades. And all that data was available to us really as the ground truth for these models. And so how we created these oracles was we do essentially 3 calculations. The first calculation I've kind of danced around a little bit is the relative distance between every product. And so we say, how closely related are these products? The second calculation is based on everything we know about these types of products. What is essentially like the worst case scenario of severity that could happen? Because again, that's going to inform our reaction. And then the third calculation that we do is really like a time series type calculation over the how the risks and customer feedback develop on these clusters of products over time. And so think about this as like we group together hundreds or thousands of products and all the customer feedback. Some of these products have a lot, some have none or very little. And we can see how this progresses to some of these products causing issues. And then we calculate a likelihood of something occurring on every product in the catalog in the forward 90 days. And we do this calculation every single week. And then what we do with that information is we trigger investigations, which are, again, these human SME investigations, ideally before any customer is exposed to a product which may carry some kind of risk. All right, and so why does this matter? Why are we doing this? So we protect customers by removing items from the store. Like, that is our role. Other people have a role of expanding selection, putting things on the store. But the products that we remove predominantly are not what you'd expect. They're not like low star rating items. They're items that just don't have much history yet. So the things that we're talking about are not, you're not often going to find them on the page 1 search results. They are emerging products, they're brand new products, or they're just tail selections, some really niche kind of products where there's not enough information there for a consumer or a shopper to make an informed decision about if it's a quality product or not. And there's not enough information for us to really risk assess what's going on. And so the reactive process that I described several slides ago is mostly filled with high volume quality products. And so the investigations that end up getting to our SME team, who are very, very skilled and experts in their products, are often filled with kind of low severity issues, kind of expected outcomes. Your computer charger heats up, things like that, or isolated incidents. It may be a manufacturing defect that has a very low likelihood of actually causing harm. And in many cases, actually, in most cases, manufacturers can provide the testing documents or product compliance requirements that enable us to put these things back up on the website. And so for this reason, kind of all that effort and all that technology only removes around 8.6% of the products we investigate permanently, which is good because it matches our hypothesis that most of the items in our stores are safe. So our opportunity, as I just described, isn't page 1. It's everything else. It's the new offerings of products, and it's a kind of tail selection that a light isn't often shown on. And so when we set out to build this risk model, the reason for it was really to augment our reactive process. But now our focus is really to replace it. And so I teased on it a few slides ago, but now over 40% of our investigations occur with no feedback at all, or sometimes months before a customer actually complains on a related or a new kind of product. So to get into the details of how we actually built this and how we perform these calculations, I'm going to invite Fedor up to the stage to go through each of these models. Here you go.
Thank you. Hi, everyone. My name is Fedor. Thank you, Chance, for the great introduction into the system and into the goals of the system. I'm a machine learning scientist in Amazon, and I'm helping various teams build our machine learning products for our internal product teams as well as our external customers. And today to you, I'm going to talk about how machine learning works behind Erica. What do you need to do to maybe understand how that works and maybe even build this for yourself or borrow some of the ideas? Well, the first thing you probably heard about machine learning is that you need data. And in order to collect data for machine learning, for this machine learning model, we had to look into the actual cases which occurred, like the investigation cases which occurred, right? We use external industry information about the product. We'll look into the customer feedback when customers reach out to us and say, okay, well, this item might have been, dangerous for me, or actually produced something bad, or broke really fast and maybe produced some smell. And also, some of the customers call us. So all of this is information which we use as a training data. And then when we launch the investigation, what happens is that the assessors actually assess a risk level for every product, right? And so we collected the 20,000 products with various risk levels, high risk levels and low risk levels. As well as we collected product attributes such as item name or brand name, and supplier attributes such as, for example, the country of origin. As you can probably guess, Amazon has a lot of sellers who sell on our platform, and various sellers buy and purchase their products in different countries, and the products are manufactured in even other countries. And all of that information is very important to understand the potential risk of every product. As well as we look into how the product was performing. Is it high attention product, a lot of people are buying it or not? And that's of course important for our prioritization of those products. And the first step in applying any machine learning algorithm is data cleaning. So what is data cleaning? Well, if you look at the data and you collected it and you think that now you have awesome data, you have terabytes of data, great, you can probably apply machine learning model. What really happens is that you need to clean your data. And what that means is that you need to understand it. You need to understand the histograms of various attributes in your data. You need to find outliers. You need to see if maybe the label, which is in our case, for example, risk level label, maybe it actually leaked into the attributes which you want to use. One of the stories I had in one of the previous applications where we tried to predict whether the product is going to be available on the platform or not, one of the catalog attributes was stock information. And there, in a free form, sometimes you actually had the leaked information about, oh, this product was out of stock on that date. And without actually thinking about what can be in that column, what can be in that information, you can just use it to predict whether the product is out of stock or not, and you're going to have awesome prediction offline, but it's never going to work in real life. So understanding this is crucial to actually build a reliable model which predicts well. And this way you're avoiding the forte of garbage in, garbage out, and you have great data in and great results out of it. So for this application, a lot of the features are text features. And what happens with text features is you need to clean them. You need to, for example, you need to remove some of the unsupported characters, right? So sellers or Amazon associates are putting information, say, with a hash or with the dollar signs between the words, and you need to remove them in order to extract the actual meaning. So let's say the battery included is a great word, which we as humans can easily understand that the hash doesn't really have to be there. But for the computer, these two words have to be separated, and it's much easier to extract information out of it. Another popular technique for text data is called stemming, and that basically, in English and in many other languages, the same words can be presented in different ways, right? You have a battery and you have the word batteries, and they carry almost the same meaning. And so we stemmed it to convert these words into batter, for example. Another important data cleaning technique which you might want to use is called is replacing missing categories and basically replacing missing data. So what happens if, for example, you don't have information about a specific category? What category is that product in? And for some reason, somebody didn't put that information in. Well, the models cannot really look at the blank and assume and get any information, because blank is not an information carrying entity. And so what you do is that you say replace that. One of the ways to do that is you replace your category with a category blank. And now it's actually a certain category which the model can say, okay, well, there's a blank category, which means it's missing. And so I can at least group all of the products with the missing category in a certain way and extract that information, or maybe don't pay attention to that specific attribute if it's not as important. For the numerical values, as you can probably guess, you cannot really replace it with blank, because all of the models look at the number and try to, build some mathematical model on the number. And when you replace numbers with blank, your models break. So instead, a popular way of cleaning the numerical attributes is to replace missing attributes with, for example, an average, or maybe the maximum or the minimum value of all of the other products. And that usually helps, but you always need to check if it does help in your application or not. The next step in applying machine learning models is feature engineering. So you can say that, well, deep learning can figure out everything about our features. I don't have to think about this. But that's actually not true in a huge variety of applications. You can't just run a deep learning model and help and think that it's going to magically find out your relationships, especially if you don't have too much data to train it on. And so this is a nice example of how feature engineering can help you. So on the image on the left, you see that there are some yellow dots and blue dots, and your goal is to separate the blue dots from the yellow dots. So what do you do? Well, evidently you need some sort of a surface. Maybe like a circle would be pretty decent. So basically, you would need the model to find that circle between the yellow dots and the blue dots. And if your attributes are x and y, then it's a very nonlinear surface. And finding nonlinear surfaces in general in math is hard. So what can you do? Well, one of the things you can do with this data is that you can say, let's replace x and y with some other features. Let's take the center of all of this data as our origin. And let's say that we're going to take the radius from that center as one of the features, and the angle as the other feature, right? So the radius is going to be one feature, and the angle is the other. And you can see on the right, that's what you get out of the transformation, right? So for the radius is x now on the right, and the y is the angle. And so what happens is that all of the blue points actually are within a certain radius around the center, and all of the yellow points are far from the radius. And the angle doesn't really matter that much. So in this case, it's extremely easy to build your classifier between the blue points and the yellow points. So what have you just done? What you've done right now is that you've used your prior information about the data, about the features, in order to extract information, help machine learning model extract that information. And that can be extremely useful in building a reliable model. So what did we do in our application? Well, we have these 200 initial raw features, such as category of the product and maybe product description. And we extracted key features, the most important ones which we thought are probably going to be most valuable. And then we've made 17 raw features, such as the product rating or product description. And then we also combined some of the features. So, for example, a good thing which really helped us in building this application is combining the price with the category of the product. So imagine now, let's come back maybe to an example of let's say battery, right? And what you do is, if you take a price of that product across the whole Amazon catalog, that might not actually tell you much. But if you instead compare that price with the average price of the category of that product, let's say that's a laptop battery for some cheap laptops. Maybe it's going to be cheap. So the information that this specific product is significantly cheaper than its neighbors or significantly more expensive is actually much more informative than just the raw price of the product. So this combination was really useful for us to build a more precise model. The deviation from say, an average price of the category. Okay, well, imagine now that you've cleaned your data, you have your features engineered, and you know everything's great. Now, how do you actually build your model? Like, how do you assess that it's good, and what methods do you use? And there are all these methods like decision trees and random forests and logistic regression. Well, the first thing you need to do is to choose a metric. In classification, for example, risky product and non-risky product, one of the most popular metrics, two of the most popular metrics are precision and recall. So precision is, imagine you have a model which predicts products to be risky or not. And precision is basically out of all of the products which this model predicted to be risky, how many of them are actually risky? So how many of them, like what's the percentage of them are false positives? So that's a precision. And recall is out of your whole catalog. You might have certain number of risky products. What is the percentage of products out of the whole risky products in the catalog you are able to capture? That's recall. And so these metrics, of course, are balancing each other, because as soon as you increase precision, you most of the times reduce recall. And the reason is that the more products you want to capture, the less precise you're likely going to be in actually capturing the right products. But a good algorithm is going to find a good balance. And how do you now you have the metrics, so how do you evaluate your method? Well, one of the popular ways is called cross-validation. So imagine that, as I mentioned, that we collected, let's say, 20,000 products with their risk levels. And you are now interested to know how your model performs on the products which it hasn't seen. So what cross-validation does is that it takes this data set, and then it says, let's take part of this data set, let's say 2/3 of the data set, and let's train my model on that. Let's basically tune my model, find the parameters, like tell it how to do on that. And then on the 1/3 of the data set which it hasn't seen, you actually try and you're estimating the metrics. So that's just training and testing procedure. And the cross-validation repeats this procedure multiple times on various splits of the data, so that you don't over-tune your model to one specific random situation where you split it that way once and then never come back to it. So it performs the split multiple times, it tests this in various ways, and as a result, you have a much more well-rounded version of how your model performs on the data it hasn't seen. Finally, for every model, you need to do hyperparameter optimization. And what that means is that, let's say you choose random forest. Well, for every random forest, you need to choose how many trees you're going to use in your random forest. And maybe the maximum depth of the trees. And there are some other parameters like which of the split criteria you're going to use. For logistic regression, you need to understand what is the regularization parameter which you're going to use in the algorithm. And these parameters are chosen during hyperparameter optimization. And the brief idea of the hyperparameter optimization is that you choose one parameter, you run cross-validation, you look at the accuracy, and you choose basically, and you do it multiple times with various values of the parameters and see what works best on cross-validation for your metrics. Finally, for a lot of business applications, you really need to look into the feature importance. So why is feature importance important? Well, that's because after you build your model, you want to verify as a business owner, is it doing something reasonable? Is it paying attention to actually important attributes? Or is it like extracting availability information from the column about the stock description or that? So one of the ways to do that is you look at the most important, all of the attributes, maybe you drop them one by one and look at how much your model performance degrades after you drop one of the attributes. And when you do that, you can see that some of the attributes, if you remove some of the attributes, the model performance degrades a lot, and for some other attributes, the model performance degrades very little, and as a result, you can actually see which attributes are more important, which attributes are less. This is one of the ways, of course, there's like plenty of other ways of calculating feature importance, but that's what we used, and found that, for example, the item name was a really important attribute, and whether the product includes a battery or does not include a battery is also a very important information piece for us. Well, now I'd like to move towards the model design and how do you actually have the model running, and what does that mean? As you can probably guess, things are not as simple as you might think from the start. And it's not like we have one model, we have one data set, we train it, and everything magically works. So what happens is that you first, on the left side of this slide, you see training inputs, and that's basically the training data we collect. And they're, of course, being fed into the model. But we don't have a single model. We have more than one model. We have three models. We have binary model, multi-class classification model, and a likelihood model. And so binary model is indicated in the slide as 1, and the multi-class classification as 3, and the likelihood model is indicated in the slide as 2. And I'm going to describe them a little bit more details later. But the idea is that the first binary model, actually, out of the huge catalog, it filters out a lot of the safe ASINs, safe products, and you're able to focus on more potentially risky products for the other two models. So this is what it does. We have a catalog of many billions of products. And if you just start training your model or even make your model look at all of that catalog and ask your model to extract very detailed information about the risk level for every single product, it might not capture it very well. And the reason is that the huge variety of safe products are going to just overwhelm the model, and it's just not going to tell you anything useful. So one of the things you can do is to filter out the most safe products out of the account, out of this process as a first step, and that's what we do. So we build this binary model which filters out the potentially unsafe products, and we end up with only a few million products. That's still a lot. You still need a lot of scalable processes to actually train those models and run those models, but it's a reduction of 1,000, which 1,000 times reduction, which is fairly helpful on the Amazon scale, as you can imagine. The next model we have is the multi-class classification model, and that model actually says for this product, for these millions of products, for every one of them, what is the level of risk? Is this a really high-risky product which might potentially, I don't know, produce some sort of a fire maybe even, or something which is dangerous? Or is this something low severity where, well, it's going to break soon and it's going to smell bad, or something like that? So we have these three levels, and now we build a multi-class classification model based on, again, item name and merchant information and the category attributes to build that multi-class classification model. For all of the models I didn't mention, but for all of the models we use random forest. That is a great classifier which often produces very good results on even small data and large data sets, and you don't need to think about the architecture of your neural network as much, so it's actually much easier to make it work, make a lot of applications work with that, and in our case that worked really well. Finally, we have this likelihood model. So the likelihood model has a very interesting nature because it's temporal. So instead of saying for every product, is this risky or not? The likelihood model is actually trying to say, is there a situation in the next, I think, 3 months, is it possible that a risky event is going to occur? Is it possible that some customer is going to reach out to us and say, this is unacceptable that you're saying this, you're selling these things? And this temporal nature requires a very different approach to actually building the features for those models. So in order to build features for the temporal models, you need to look at the temporal information, such as recently, how much this product was sold, how much this product was looked at, like by the detailed page clicks. What was the recent price of that product? What was the recent rating of that product? And did things change much from the past? And in order to build that training data set, instead of collecting it once, you actually need to collect it across time. So we took 2 years of data and we collected, I think, 7 snapshots of this data in order to evaluate thoroughly on during every season, January, or whether it's winter, whether it's summer, whether it's January or September, or whether it's autumn or fall. You evaluate how well this model performs at every time of the year where you want to apply it. And so for that model, again, this is a classification model. It's just the type of the data which has been fed into it is different. And we've used random forest with this temporal information to predict the likelihood of some event occurring in the future. Now I'm going to pass the talk to Wei, who's going to tell you how such a system, such a model, and such a system for detecting risk can actually function on Amazon scale in production. Thank you.
So thanks, Fedor. Hello, my name is Wei. So I'm the senior product manager for machine learning product within safety and compliance. So I lead the development of Erica from the initial concept to the final implementations. So today, I'm kind of really happy to walk you through the rest of the presentation. So to talk about the production system and also to share some of the success story with you guys. So I still remember like when we complete the data processing and model design, I talked to Fedor, says, dude, let's have a happy hour. And Fedor says, no, dude, it's not time. I mean, production system is more challenge. And he was right. So, but no worry, Fedor, we can have the happy hour, in Las Vegas. So the key challenge, for the production system is about 2 words. So we can summarize that into 2 words. The first word is about scaling. It's because when you build a model, when you do the data processing, you do your model in a really small scale. So you probably only deal with like thousands of training data and also probably like several thousand of like the model feature. It's kind of manageable in the testing environment. But when you implement your model into scale, especially you consider the amount catalog scale, it's become kind of really challenging. So that's why the really key things we want to address for our product system is scaling. So that's the first key things. The second key things is regarding the automation. So the whole product system is really long. So you have your data input to the model, and the model do the data cleaning and make prediction. And then so you have a way to upload data to your storage. And then so you also, your storage point is connected with some of the system for it to consume and to perform actions. So ending all the steps here, you want them to be all automated. You don't want any like a human intervention. You don't want someone manually do something in the process. So the automation is the second key for our product system. So probably you'll hear a lot about like scale and automation in my next following slide. So this is kind of like at high level. So what is our production system looks like? So the first component we have is what called is like the data sourcer. So this is like an input end for our system. So basically, so how you get like the billions of like model feature and the product attribute and to collect this information and for your model to consume. So that's kind of the first part of the product system. And then we have our model executor. So we have our binary model executor. So which, as Fedor mentioned, is make the prediction like whether potential unsafe or potential safe. And then we also have like the executor for the multi-classification and also for the likelihood model. So which will predict what is the severity and what is the likelihood of the product. So the data source will input the information into the executor to perform like the predefined data cleaning and make the prediction. And then the next component is what we call is the uploader. So you may be curious like why you need a special component to help you just upload the data. Well, if the data is really small, you don't need it because so it's really manageable. So you just can directly upload the data to your storage. But here we talk about like hundreds of millions of results, the prediction on every week. So we need to have like a really special component to monitor the upload status, to make sure you won't overloading your service, otherwise you'll get a problem. So the last part of the process is we call the storage. So this is the place you storage all your prediction result, and also you be able to share the result to some like a search UI. So the non-technical person can go to the search UI and perform the search, get a result, and perform some analysis. And also this storage point should be flexible enough so you can connect to your service. So like for us, we connected to our investigation service to help us to perform the product investigation. So when Erica detect like a high severity and high risk product. Let's go deeper. So the first is the data sourcer. So for the data sourcer, as mentioned, is kind of like common to help you to collection your model features and your product attribute, for the model executor to consume. So our data sourcer is hosted in AWS Redshift. So AWS Redshift is like a fast, scalable data solution that can help you to analyze your data across your data warehouse and a data lake. So So we host our data source in AWS service, and then so we collect all the information. And once we collect information, so we'll temporarily store information in AWS S3 bucket. So S3 stands for Simple Storage Service. So we temporarily store the information in the S3 location, and then so wait for the model executor to consume. So our data source is built at scale. So that's why we're able to process billions of model features when we build a model initially. And also, we're able to process the weekly data upload every week. So this is also like hundreds of millions of product, every week. So it's really heavy data log. The next component is the risk model executor. So when you build the risk model executor, probably you'll ask yourself a lot of questions. So like how we can, to build this, scalable, to be able to process the billions of model features come from data source, how we can make sure it's really efficient, and we can optimize, in terms the effectiveness of the system to make sure it can process all the data within the time we want it to, within the certain, SLA, the service level agreement. So to respond to all these changes, so we build a risk model executor. So we have like a variant model executor, and we have the multi-classification and the likelihood model executor. So basically, for all this executor, is hosted in Amazon ASG. ASG stands for Auto-Scaling Group. So Auto-Scaling Group is like a collection of Amazon EC2 instance. So EC2 stands for Elastic Cloud Computer. It's like a service. So it's a collection of EC2 service. So that can that's work as a collection of a logic grouping. That's for the purpose of scaling and also management. So we host the executor in the ASC service. So the beauty of ASC, because it's dynamic. So for us, so we have always a standing by EC2 instance to just continually export for data. So if we have the data from data source, but once we have a large data load from the data source, then we'll scale up the process. So we can scale up to as many instances as we want to be able to process the data volume that is required. So for us, due to the flexible design and the scalability, so we are able to process hundreds of millions of data feature within 2 days. So that's why for Erica, it's be able to to publish the weekly prediction result across the whole Amazon catalog. So the next component is uploader. So as I mentioned, so because we have billions of prediction results, we need a component to really help us to upload the result to the storage. So to be able to manage the upload rate, so we use a component called AWS CloudWatch Monitor. So what it do is actually help to managing your upload metrics. So basically, it can tell you what kind of speed you have now, whether it's overloading or not. So we use this component to help us to monitoring the upload status. So here's how it works technically for the uploader. So we have the result from the risk model executor. So we get the results. So we get all the prediction result, and then again we use Amazon S3 bucket to temporarily storage the result, and then so the uploader get the information, consume the data from the S3 bucket. So then it starts to uploading. So again, based on the CloudWatch Monitor, so we are be able to adjust the thread or instance we're going to use to upload data. So for example, now if the system say, oh yeah, now you have billions of billions of prediction result you need to upload. So then we'll increase the thread, and then so we'll perform the uploading in a more efficient way. And also the most important things, so just avoid to overloading your service. So that's really critical for the production system. Okay, so the last component is we call the storage part. So that is we build Erica to be able to storage all the results. So first, so we kind of ask ourselves like, what would be a storage, solution? So first, so it should be able to make it easy enough for the user to search all the predict result, right? So you should have like a service dashboard. They can filter all the data, so they want to search. Like probably they want to see what is the product name, so what is the product category, and also they want to filter by the severity level. They want to filter by in terms like the likelihood. So this should be really easy enough for the non-technical people like our SME, subject matter expertise, to be able to search for the results. And also the other really important, for the storage point, as I mentioned earlier, it should be really kind of flexible enough. So it can help you to adjust, to help you to use, as a connection point to the various service you have, and you'll be able to use that result and to perform your actions. So that's why, so based on our criteria, based on our in terms like the things we want to choose, we choose Elasticsearch, AWS Elasticsearch, as is like our ideal storage point. So because for Elasticsearch, so it has like a built-in like plugin. It's called Kibana. So this is kind of like a self-service dashboard. So you can define the things you want to search. You can feel free to add a data point you want to get the results. And then it's kind of really user-friendly. So for like our SME, they love it because it's really simple to use to get the result and help them to perform the risk assessment and also to understand what is the product trend risk. And the other things, as mentioned, so it's kind of acting as a connection point to connect to our investigation service. So then we can to use that signal to trigger the proactive investigation as mentioned by Chance. So when Erica detects like a high severity and high likelihood product. So now I'm kind of like really kind of exciting to share you guys with two success stories. We have for Erica. So to understand what is the real world impact for Erica. So the first story I'm going to share is about the proactive investigation, as we talked about several times. So it's kind of investigation we trigger ahead of the customer report concern. The second thing I wanted to share is like the holiday peak support. So basically, we support the holiday peak preparation before it's come. So this is kind of a really well-known example, the iceberg model. So for that model, it's basically saying, so most of the things you see is only the minority of the issues. So you can only see the issue from the top. So this probably is not, the big issue. And the majority of the issue is kind of underwater. So it's similar to the task of Erica or the task of like a proactive investigation. So we want to use the Erica as a tool to effectively investigate or take actions for the majority of the risky product. So it has like two advantages. So the first advantage, as Fedor explained and also Chance explained, is cascading the risk to similar product. So that means when we perform the investigation, we also consider similar product instead of like just one single product. So like one example I can provide is like so we have received like one concern for a baby product. So that's probably can refer to the top. It's only one issue we receive for the product. But we use Erica to detect and scan the whole catalog, and then we took actions against 600 products that has similar issues over the same period. So that's kind of a really good example to show how we cascade the risk to similar product. The second advantage of proactive investigation is we can trigger the investigation ahead of the customer concern. So here is a real example. So last year on March 28th, so Erica detected a product so with 95% of likelihood of causing a safety concern in the next 3 months. So on the same day, we took actions. We suppressed the product. And guess what? After 1 month, which is the April 20th, we actually received an incident, for this product. So you may be kind of curious, like why, you still receive the instant. So this is because, before we took the actions, the customer already purchased the product. So that's why, we kind of haven't provided this kind of concern. However, so this became a really good example to show like how Erica can see the future, predict the future, and then notify us to take the actions. So the other, success story I want to share with you guys is the hot peak support. So as I mentioned, so we perform the proactive investigations through the whole year. And also we support, the holiday preparations ahead of time. So because we know, normally before the holiday peak, so there's like hundreds or millions of new product listed in the catalog. So majority of them is kind of really safe. So we need to have a way, and also the business team say they really want to need the help from us to help them to identify the minority of the unsafe product. There may be only like a few hundreds, but they need a tool really effective to help them to identify this kind of risky product. So here is kind of really good example. So basically in Q4 2017, so before the holiday peak, we used Erica to scan the whole catalog, and we identify few hundreds of risky products that may be cause problem. And after our investigation, so we found out 82% of them is actually will cause some issue. So that's why we're taking down the product. So then, we did some like analysis based on the concern rate. So the concern rate is the number of complaints divided by the 1 million units sold. So as you can see here, so the blue line is the concern rate for 2018, and the red line is the concern rate for 2017. So after we took the suppression actions for this high risky product, so the concern rate decreased dramatically. So when we compare like a year over year, so we found out we have like 78% year-over-year reduction. So this is amazing, right? Compared to the hundreds, millions product listing, we only action on a few hundred, and we have really big impact in terms of our concern rate. So most of what I just described, just like one of the machine learning product I manage. So we use the data pipeline, the service, the structure of Erica. So we also develop some other really interesting product. So this product is what we just described, like for Erica. So we have the prototype, and then we launch the product to help us to identify the risky product. And then based on the algorithm and also the data structure we have, so we built another model called the Erica Emerging Risk. So this one can help us to identify the product category with, accelerating, interesting, or like will be become like a trending product. So we use some like the data like the offer density and also search trend as the trending data to train the model to be able to identify the product category trend. So because what we notice, so for the same product, if you have a lot of seller listing the offer against it, so that means it's become popular. And also what we notice is normal before this product become really popular, the search trend, both internal, like our Amazon internal search, and also the Google search. So you can see a spike for this product category. So that's why we use the offer density, we use the search trend together with some like safety consideration. So we build this Erica emerging risk model to be able to identify some like a really popular and maybe cause some issue like a product category. So one example is like the eye clip glass. So basically, so we're trying to build a model to detect some like the eye clip glass before this kind of eye clip event and try to do some control. So the next product we developed is what we call Erica classification. So basically, we use our relativeness model, and also with some like a clustering algorithm as well. We develop our Erica classification model. So for this model, it's able to classify the product in our catalog. So for example, if you say I want to know how many USB cable is in Amazon catalog, you'll be able to use Erica classification and to classify all the product in the catalog. So that's kind of really kind of like a scalable and efficient tool in terms of classification. So the things we're doing now is like we want to expand Erica to more broadly. So we want to, expand Erica to the marketplace or the country Amazon exists. And also the other things we are doing at the moment is like we build a model called Erica Technical Compliance. So instead of like predicting the risky product, safe or unsafe, so we also want to have a model to predict the compliance risk. So most of the compliance risk is like the labeling issue. So whether the product may missing the label and be cause some like long compliance issue or not. So that's kind of like the model we are trying to build to predict that kind of risk. So that's all our presentation. Hope you guys enjoying our presentation in the last 1 hour. Thank you so much for joining. Any questions?